Alright, let's look at some reactions of phenols. The first one is a Williamson ether synthesis. This is very similar to the reaction we looked at back in Organic 1 Test 3. And what we're looking at here is the deprotonation of a phenol. And the phenol can be deprotonated by pretty much any base. I've got sodium carbonate here as a base, but sodium hydroxide will work as well. And the first step is just taking the H off that and leaving a negative charge on the oxygen. Then we can get an SN2 reaction to occur, but generally we use just the primary alkyl bromides here because the other ones tend to lead to elimination products. So this O negative comes in and kicks out the Br in a typical SN2 reaction, which we would only really do on a primary substrate anyway, and we end up getting an ether, a phenyl ether specifically, where the benzene group is attached to the oxygen. In the Colby synthesis, this is a way that we can make salicylic acid, which is a precursor to aspirin. And the way this is made is that the phenol is deprotonated using some kind of base. We've got sodium hydroxide here. And then we can react it with carbon dioxide. That's usually in the form of dry ice. That's just solid carbon dioxide. Just throw that straight into the reaction as a solid. And it will react with the anion from the phenol. Now remember, these phenols are quite acidic, and the reason they're acidic is because the anion is stabilized by the aromatic ring. We'll see a lot more of that later on. And then so the anion of the phenol can then react with the carbon dioxide. It always reacts at the ortho position to the OH, and that's because of the way that these arrows are going. We don't usually get reaction down here at the para position. And then we get the salicylic acid after a number of steps. In the Reimer-Tiemann reaction, we can get salicylaldehyde. So instead of the acid group here, we can get the aldehyde group. And we do this by using a dichlorocarbene intermediate. And the dichlorocarbene is formed from chloroform in excess KOH with some heat. Dichlorocarbene is a very electron deficient species, so it will react with something that's got lots of electrons, like this phenoxide ion. Now, as I said earlier, these things are fairly acidic, so it's pretty easy to remove this hydrogen. Then the negatively charged ion can then react with the electron deficient dichlorocarbene species. After a number of steps, we can end up with our salicylaldehyde as a product. And again, the reaction is specific at the ortho position.